Welcome to homework.
Okay, so for this problem, we're talking about iodine decaying. Um, and so we're wondering about the activity in this many micrograms of it. And so, yeah, before I get going, I'll just say that I'm going to do everything in units of days. Like I chose that for the timing. I don't think the problem specified if you should use seconds or not. I just chose that because to alleviate the astronomicalness of the numbers, because like we're working on scales of like months and hours, and so days is kind of in between, but you can of course convert anything that you need to. Okay, so let's get going. So we want to get the activity at time equals 0. So that's going to be dn dt evaluated at time equals 0. And if you're in general, the number is going to be the initial number times e to the minus t times lambda, where lambda is this log of 2. I think they give it in the book, 0.6 something times t 1/2. Okay, and then anyway, if you take this derivative, then the magnitude of dn dt, oh yeah, it should be the magnitude. Oof. Lots of vertical lines. Okay, dn dt is then just this lambda times m naught and naught. Okay, great. And so that's what our goal is to evaluate, is this quantity. We need to know the half-life, and the half-life is, I looked it up and it was 8.02 days. So I'll kind of put that on this line here. This is like my prep area. So T is 8.02 days. Okay, and then I'll put this prep area in a box. And then one other little thing I want to do is we want to get the initial amount of particles. So that's kind of also like a side calculation. And so you want to use the molar mass of iodine. And so we want the molar mass, I think as m sub m is the subscript, is 261.8 grams per mole. And then if we want to now we kind of want to convert that to like how many inverse particles there are, given that there's this many grams per mole. Maybe a more clear way to start off would be to actually start with the amount that they give us. So that's 782 times 10 to the minus 6 grams. And then now we want to multiply that by, or divide it by 261.8 grams per mole. And then Avogadro's number, particles per mole. And then we'll end up with the number of like nuclei or particles. And so when I multiplied all that out, I got it. And the initial n, so that's our n naught, is equal to 1.80 times 10 to the 24 particles. Okay, and then now we just need to get the initial number activity, we just need to multiply that by lambda. So lambda I got was, so it's the ln of 2 divided by 8.02 days. And so we can say that it's, what is lambda? Oh, I don't think I actually wrote, let me actually calculate this. I don't think I actually did. So ln of 2, forgot to use 0.02. Okay, so that's 0.086 inverse days. oops, that's supposed to say day to the -1. Okay, yeah. So that's our lambda, and then now, now we're prepared to actually calculate everything. So R naught is equal to, let's see, what was it? Oh yeah, N naught times lambda, using the N naught and the lambda that I calculated. Oh, that slash never went away. Sorry about that. Okay, anyway. So just multiplying those two numbers, the 1.8 10 to the 24 times 0.086 inverse days, I obtained that this was 1.55 times 10 to the 23 like decays per day, or particles decaying per day. And then to evaluate it at other times, you want to use the more general equation, R naught e to the minus t over, or t times lambda. And then so if I use, for B, we're trying to get it for 1 hour. So 1 hour is 1/24th of a day. And so plugging that in to here, and then again using the same lambda and this R naught, I obtained that R was equal to, oh, it was like really similar, because I mean, you're barely into the half-life. Let me go look at what I got when I did that. I guess it's basically stayed the same, 155 10 to the 23. So I mean, basically the same, but let's see, let me add some more sig figs so that they're actually different. So the first one would be 1.555. So let me add in another 5. And then this one would be 1.550. So not much of a change. Times 10 to the 23 particles per day. Okay, and then for the next one, when you actually start waiting many months, then you get, you just want to use T as, if you do 30 days a month times 4 months is 120 days. Oh, what happened to my 0? 120 days into this equation, again, with all the same lambdas and R naughts, and I obtained that R was 4.74 times 10 to the 8 decays per second. So it's really, as a proportion, it's really not decaying much. Let me just double check on my numbers. Oh, 18. I'm glad I caught that. I was like, wow, that seems like a huge reduction. 18.